Welcome! In this session, we'll tackle an interesting problem titled Replace Words. This problem challenges us to optimize string replacement using a dictionary of roots. Stay tuned as we explore the intuition, approaches, and techniques to solve it efficiently. In this problem, we are working with the concept of root words in English. A root word is essentially the base form of a word, such as act, which can be extended to form words like acting or actor. Here, the task involves using a dictionary of root words to simplify a given sentence. Specifically, if any word in the sentence contains a root word from the dictionary as its prefix, we replace that word with the root word itself. For example, if the dictionary contains the root word act, then words like acting or actor in a sentence would be replaced with act. The goal is to process the sentence so that each word is replaced with the shortest matching root word from the dictionary, or left unchanged if no match exists. Now, let's look at the input and output formats for the problem. The input consists of two parts: a list of strings, called the dictionary, where each string represents a root word, and a sentence, which is a string of words separated by single spaces. The task is to produce a single output string, where the sentence has been modified by replacing words with their shortest root words, if applicable. If no root word matches a word in the sentence, that word is left unchanged. For example, consider a dictionary of root words such as cat, bat, and rat, and a sentence like, "The cattle was rattled by the battery." The output for this input would replace cattle, rattled, and battery with cat, rat, and bat, respectively, resulting in the modified sentence, "The cat was rat by the bat." To break down the first example, the root word cat matches the prefix of the word cattle, so cattle is replaced with cat. Similarly, the root word rat matches the prefix of rattled, which leads to replacing rattled with rat. Finally, bat matches the prefix of battery, so battery is replaced with bat. Any words in the sentence that do not have a matching prefix in the dictionary remain unchanged. In another example, with a dictionary containing the root words a, b, and c, and a sentence like adsfas fabs bab cadsfafs, the output becomes aabc. Here, each word in the sentence is replaced by its shortest matching root word of 4 adsfas, b 4 absbs and bab, and c 4 cadsfafs. In the third example, we have a dictionary with root words abc and def, and a sentence ghijklmnopqr. Here, no root word in the dictionary matches the prefix of any word in the sentence. As a result, the sentence remains unchanged, and the output is simply ghijklmnopqr. This highlights an important scenario where none of the words in the sentence have roots from the dictionary, and the function needs to handle such cases gracefully by leaving the sentence as it is. Finally, let's consider the constraints and edge cases for this problem. The dictionary can have up to 1,000 root words, and each root word can be up to 100 characters long. The sentence can be as long as 10,000 characters, and it will only consist of words separated by single spaces. Both the dictionary and the sentence will contain only lowercase English letters. Edge cases to handle include an empty dictionary, where the sentence remains unchanged, and sentences where no words match any dictionary roots, which also leave the sentence unchanged. If a word has multiple possible root matches, it should be replaced with the shortest root. Additionally, for long sentences approaching the upper character limit, the solution must remain efficient and performant. To start, let's consider a straightforward but inefficient method, the brute force approach. Here, the idea is to iterate over each word in the sentence, and for every word, compare it against all the roots in the dictionary. If a root matches the beginning of the word, we replace the word with the shortest matching root. The process involves 3 steps. First, checking each root in the dictionary to see if it's a prefix of the current word. Next, we track the shortest matching root, if any. Finally, the modified word is appended to the result list. While this approach is simple to implement, it's computationally expensive. The time complexity is O(m*n*k), where m is the number of words in the sentence, n is the number of roots in the dictionary, and k is the average length of a word. The space complexity is proportional to the result list size, O(m*k). The trade-offs here are clear. While easy to understand, this method becomes impractical for large inputs due to the redundant prefix checks performed repeatedly for each word. Now, let's move to a more efficient solution, using a tree data structure. The intuition behind this approach is to eliminate the repeated prefix checks by storing all roots in a tree, which is a tree-like structure optimized for prefix lookups. This allows us to find prefixes in O, K, time, where K is the length of the word being checked. The steps are as follows. First, we build the tree from the given dictionary of roots. Then, for each word in the sentence, we traverse the tree to find the shortest root that matches the word's prefix. If such a root exists, we replace the word with it, otherwise, the original word remains unchanged. Finally, the processed word is appended to the result. The time complexity here is O, n asterisk k plus m asterisk k, where n is the number of roots, m is the number of words in the sentence, and k is the average word length. Space complexity is O, n asterisk k, for the tree. The key trade-offs are that while this approach is highly efficient for large inputs, it requires additional memory to store the tree. However, the benefits of avoiding redundant computations far outweigh this cost. An alternative strategy involves using a hash table for prefix matching. Here, we store all the roots in a hash table, such as a Python set, and use prefix matching to replace words. For each word in the sentence, we generate all possible prefixes and check if any of them exist in the hash table. If a match is found, the word is replaced with the shortest matching prefix. In terms of complexity, this approach is similar to the tree method, with a time complexity of O, n asterisk k plus m asterisk k, and a space complexity of O, n asterisk k, for the hash table. While this method is slightly simpler to implement than a tree, it has its own drawbacks. Generating prefixes for every word adds overhead, and the process may not be as efficient as a tree for large dictionaries or sentences. Additionally, the lack of a structured hierarchy, like in a tree, means we lose some of the natural optimizations that come with direct traversal. After evaluating the options, the optimized tree-based approach stands out as the best strategy to solve this problem. Its efficiency stems from the fact that it directly leverages the prefix nature of the problem. By storing all roots in a tree, we can quickly traverse to find the shortest matching prefix for each word, avoiding redundant checks and unnecessary computations. This approach guarantees that the shortest prefix is found first, thanks to the structure of the tree. The aha moment here is realizing that prefix matching is inherently suited to trees, which are designed to handle such problems efficiently. Compared to the alternatives, the brute force method is too slow and impractical for larger inputs, while the hash table approach, though viable, introduces overhead from prefix generation. The tree strikes the optimal balance between time and space, scaling well while maintaining clarity and efficiency. This makes it the ideal choice for handling large dictionaries and sentences in a performance-conscious way. Here, we're tasked with replacing words in a sentence with the shortest root from a given dictionary of roots, but only if the word starts with that root. For example, if we have the dictionary, cat, bat, rat, and the sentence, the cattle was rattled by the battery, the result should be the cat was rat by the bat. To achieve this, we can break the problem into three main steps. First, we parse the input, which includes the dictionary of roots and the sentence. Second, we use a brute force approach to iterate over each word in the sentence, comparing it to all roots in the dictionary to find and replace with the shortest matching root. Finally, we construct the output sentence by combining the transformed words. Let's explore these steps in detail, starting with the initialization phase where we store the roots, split the sentence into words, and prepare a list for the transformed output. Once we've initialized our variables, we then iterate over each word in the sentence. For each word, we initialize a variable to track the shortest matching root. We then compare the word with each root in the dictionary using the starts with method. If the word starts with a root, we check whether this root is shorter than the previously found matching root. If it is, we update our shortest matching root. After examining all the roots, if a matching root is found, we replace the word with this root. If no match is found, we simply keep the word as it is. We then append the transformed word to our output list. Once all words have been processed, we construct the final output sentence by joining the transformed words together with spaces, and this modified sentence is returned as the result. Let's take a closer look at some key insights into this brute force algorithm. First, the time complexity. For each word in the sentence, we compare it with every root in the dictionary. If there are n words in the sentence and m roots, the overall complexity is O, n asterisk m, which can become inefficient for large inputs. However, the algorithm guarantees correctness since it explicitly checks all roots for each word and ensures the shortest matching root is selected. Next, we consider edge cases. If a word in the sentence has no matching root, it remains unchanged. If roots in the dictionary share overlapping prefixes, like cat and cattle, the algorithm will still correctly select the shortest root. If the dictionary is empty, the sentence remains unaltered, and if the sentence itself is empty, the output will simply be an empty string. To implement this algorithm, we utilize specific data structures. First, the dictionary of roots is stored as a list, allowing us to iterate over all roots when processing each word. Next, the sentence is split into a list of words for easy manipulation and transformation. Finally, we use an output list to store the transformed words as we process the sentence. Once all transformations are complete, this output list is joined into a single string to produce the final result. These straightforward data structures are sufficient for the brute force approach, but we'll soon see that there are ways to optimize the algorithm using more advanced techniques. Let's now explore a few optimizations to make this algorithm more efficient. One simple improvement involves sorting the dictionary of roots by length in ascending order before processing the words. This ensures that the shortest root is encountered first, eliminating the need to track and compare root lengths manually. A more advanced optimization involves using a tree data structure. By building a tree from the roots, we can traverse it for each word to quickly find the shortest matching root in O, K, time, where K is the length of the word. This reduces the overall complexity to O and *K, which is significantly faster than O and *M for large dictionaries. Additionally, we can implement early termination within the root search. Once we find a matching root, we can immediately stop further comparisons, assuming the roots are sorted by length. These optimizations enhance the efficiency without compromising correctness. Let's walk through a complete example to solidify our understanding. Suppose the input dictionary is cat, bat, rat, and the sentence is the cattle was rattled by the battery. First, we split the sentence into a list of words, the cattle was rattled by the battery. Now, we transform each word. The word that has no matching root, so it remains the. The word cattle matches the root cat, so it becomes cat. The word was has no matching root and stays as was. The word rattled matches the root rat, so it becomes rat. The word by has no matching root and remains unchanged. Finally, the word battery matches the root bat, so it becomes bat. Combining these transformed words, the output sentence is the cat was rat by the bat. This is the modified sentence returned by the algorithm, demonstrating how the shortest roots were correctly applied to the input sentence. Here, we are implementing the solution by breaking it down into clear steps. First, we create a tree, which is a tree-like data structure, to store all the root words from the given dictionary. This allows us to efficiently search for the shortest root later. We start by initializing an empty dictionary to represent the tree. For each root word in the dictionary, we iterate over its characters, adding them to the tree if they don't already exist. Once all characters of a root are added, we mark the end of the root word with a special symbol, in this case, the hashtag character. This helps us identify when we've reached the end of a valid root in the tree. Next, we define a helper function, findRoot, which is responsible for finding the shortest root word for a given word in the sentence. This function starts at the root of the tree and iterates through the word's characters. As it traverses, it builds a potential root string. If a character is not found in the tree, we stop searching, as no matching root exists. However, if we encounter the hashtag symbol during traversal, it means we've found a valid root, and we return it immediately. If no root is found by the end of the word, the function simply returns the original word. Now, with the helper function in place, we move on to processing the sentence. The sentence is first split into individual words using the split method. For each word in this list, we use the findRoot function to determine whether the word can be replaced with a shorter root. This is achieved by using a list comprehension, which applies findRoot to each word and stores the results in the replaced _words list. Finally, we join these replaced words back together into a single sentence using the join method, with spaces separating the words. The completed sentence, with all necessary replacements applied, is then returned as the result. Here, we begin by importing the necessary packages and defining our solution class. The main method, replaceWords, takes two inputs, a list of root words called dictionary and a sentence. The goal is to replace words in the sentence with their shortest root from the dictionary, if one exists. To achieve this, the first step is to build a tree data structure to store the root words. We initialize the root of the tree as a new tree node. For each word in the dictionary, we iterate through its characters. If the character doesn't already exist in the current node's children, we create a new tree node for it. Then, we move to the next node. Once the word is fully inserted, we mark the end of the word by setting isEndOfWord to true. This tree will help us efficiently search for the shortest root of any word later. Next, we define a helper function called findRoot to locate the shortest root for a given word. Inside this function, we traverse the tree character by character, appending each character to a string builder as we go. If we encounter a null child or reach the end of a root word, we stop the traversal. The findRoot function then returns the root word as a string if we ended at a valid root, otherwise, it returns the original word, meaning no root was found. Moving on, the next step is to process the sentence. We split the sentence into individual words using the split method and initialize a string builder to construct the result. For each word in the sentence, we use the findRoot helper function to retrieve its corresponding root, if it exists. If the result string builder already contains text, we append a space before adding the next word. Finally, after processing all words, we convert the string builder to a string and return the modified sentence. At the bottom of the code, we define the treeNode class. Each node consists of an array of 26 children, representing the lowercase English letters, and a boolean isEndOfWord to indicate if a node marks the end of a root word. This structure ensures that our tree is both space-efficient and easy to traverse when searching for roots. In the replace words problem, the goal is to replace words in a given sentence with the shortest possible root from a dictionary. If no root matches a word, the word remains unchanged. To solve this efficiently, we use a data structure called a tree, which allows us to store and search for roots quickly. For example, if our dictionary contains the words cat, bat, and rat, we start by building the tree. We begin with an empty tree and insert each word one by one. First, we insert cat, resulting in a nested structure where C leads to A, and A leads to T, with a marker indicating the end of the word. Next, we insert bat, adding a new branch starting with B, and finally, we add rat, creating another branch under R. This process builds a compact representation of the dictionary for fast lookups. Once the tree is built, we process the sentence by splitting it into individual words. For each word, we traverse the tree to find its shortest root. For instance, starting with the word the, we find no matching root in the tree, so it remains unchanged. For cattle, we follow the tree nodes for C, A, and T, identifying cat as the root, so cattle is replaced with cat. Similarly, rattled matches the root rat, and battery matches the root bat. Words like was and by have no matching roots, so they remain as they are. After processing all the words, we join them back into a sentence, resulting in the cat was rat by the bat. This output matches the expected result. In another example, if the dictionary contains the words AA and AAA, and the sentence is the quick brown fox, we start by building the tree. First, we insert A, creating a single node with an end marker. Then, we insert AA, extending the tree with an additional level for the second A. Finally, we add AAA, adding yet another level to the tree. This structure allows us to store all three roots compactly while maintaining the hierarchical relationships between them. With the tree ready, we process the sentence the quick brown fox by splitting it into words. For each word, we attempt to find the shortest matching root in the tree. However, none of the words in this sentence, the quick, brown, or fox, have matching roots in the dictionary, so each word remains unchanged. After processing, the replaced words are identical to the original, the quick, brown, and fox. Joining these words back into a sentence produces the result, the quick brown fox, which reflects the absence of applicable replacements. Now consider a dictionary with words look, looked, just, and like, and a sentence she looked just like her mother. To begin, we construct the tree by inserting look, creating a branch for L, O, and K. Then, we insert looked, which extends the look branch with additional nodes for E and D. Next, we add just, creating a separate branch under J, and finally, like, adding another branch under L that diverges from look. This structure efficiently represents all roots in the dictionary and their relationships. With the tree in place, we process the sentence by splitting it into words and finding the shortest root for each word. For she, no root is found, so it remains unchanged. For looked, we traverse the tree and identify look as the shortest root, replacing it. The word just matches the root just, and like matches the root like. Words like her and mother have no matching roots, so they stay the same. After replacing applicable words, we join them back together, resulting in the sentence she looked just like her mother, which is the final output. When analyzing the time complexity of this solution, we start by looking at the process of building the tree. In this step, we insert all the root words from the dictionary into the tree. If there are n root words and each has an average length L, the insertion process involves iterating through each character of these words. This gives us a time complexity of O(n*L) for this step. Next, we consider the process of finding the shortest root for each word in the sentence. If the sentence contains m words and each has an average length k, the worst case involves traversing up to k characters in the tree for each word. This results in a time complexity of O(m*K) for this step. Following the replacement process, the final step is to concatenate the replaced words to form the complete sentence. This involves iterating over all m words in the sentence, which has a time complexity of O(m). When we combine all the steps, the overall time complexity is the sum of these components, O(n*L) for building the tree, O(m*K) for finding the shortest roots, and O(m) for joining the words. Therefore, the total time complexity of the solution is O(n*L) plus m*K. Now, let's examine the space complexity. The primary space usage comes from the tree built to store the root words. In the worst case, where no prefixes are shared, the tree requires O(n*L) space, since each character of every root word is stored. In the best case, where all root words share a common prefix, the space required for the tree reduces to O(L). Additionally, while processing the sentence, we store the replaced words in a result array. This requires O(m*K) space in the worst case, where m is the number of words in the sentence and k is the average length of these words. Combining these, the overall space complexity is O(n*L) plus m*K. To better understand the efficiency of our approach, let's compare it with a naive solution. In a naive approach, we would iterate through all n root words for each of the m words in the sentence to find the shortest prefix. This results in a time complexity of O(m*N*L), where L is the average length of a root word. The space complexity of the naive approach is O(1), as no additional data structures are used. In contrast, our tree-based approach has a time complexity of O(n*L) plus m*K, and a space complexity of O(n*L) plus m*K. This demonstrates that the tree-based approach is significantly faster for large inputs, as it avoids repeatedly scanning the dictionary for each word. Finally, let's analyze the best, average, and worst-case scenarios. In the best case, where root words share many prefixes, the tree's space usage reduces significantly. The time complexity remains O(n*L) plus m*K, but the space complexity approaches O(L) plus m*K due to the shared structure of the tree. In the average case, we maintain the same time and space complexities of O(n*L) plus m*K. In the worst case, where no prefixes are shared among the root words, the space complexity of the tree reaches its maximum at O(n*L), and the time complexity remains O(n*L) plus m*K. These guarantees make the tree-based solution both efficient and predictable across different input scenarios. When tackling the replace words problem, there are several common mistakes to watch out for. First, failing to sort the dictionary of roots in lexicographical order can cause issues. For example, you might end up replacing a word with a longer root when a shorter one exists. To avoid this, always prioritize the shortest root by sorting the dictionary or using a tree for efficient prefix matching. Next, inefficient string matching is another pitfall. If you use nested loops to compare every word in the sentence with every root, the time complexity becomes O(n*M), which is impractical for large inputs. Using a tree can significantly optimize this process. Another critical mistake is partial matching bugs, where a solution replaces a word with a root that's only a substring, not an actual prefix. For example, replacing cats with cat is valid, but replacing cats with rat is not. Ensure that your solution checks for actual prefixes. Finally, don't overlook edge cases. Words with no matching roots should remain unchanged. Overlapping roots like cat and cater must be handled carefully, and empty inputs, whether the dictionary or the sentence, should not cause errors. These details are crucial for a robust solution. Another mistake to avoid is modifying words incorrectly due to case sensitivity or punctuation. For instance, cat with an uppercase C shouldn't match the root cat unless your solution explicitly accounts for case insensitivity. Similarly, punctuation can interfere with matching if not handled properly. Beyond common errors, there are insights to keep in mind for interviews. This problem is a great example of prefix matching, a recurring theme in tasks like autocomplete, spell checking, and domain filtering. Be ready to discuss tree-based solutions in detail, including their construction and why they're efficient. You should also be prepared to weigh trade-offs. While tries offer O(n) lookup time for prefixes, they consume more memory. In contrast, a hash set or brute force may be sufficient for smaller inputs. Interviewers often look for you to recognize when to optimize, for instance, transitioning from brute force to a tree or sorting, and to clearly articulate your thought process. Finally, clarity is key. Explain how your solution handles edge cases, and justify why you chose a particular data structure. This demonstrates both problem-solving skills and attention to detail. For further practice and to deepen your understanding, explore related problems. These include LeetCode 648 itself, LeetCode 208, which focuses on implementing a tree or prefix tree, LeetCode 720, where the goal is to find the longest word in a dictionary, and LeetCode 1268, which involves creating a search suggestion system. Each of these problems highlights different aspects of prefix matching in tree usage. When considering alternative approaches, the tree-based method is one of the most efficient for this problem. By constructing a tree from the dictionary of roots, you can traverse it for each word in the sentence to find the shortest matching prefix. This approach has a time complexity of O(n) plus m, where n is the total number of characters in the dictionary and m is the total characters in the sentence. The main advantage of using a tree is that it avoids redundant comparisons, making it ideal for large inputs. However, the trade-off is higher memory usage, which might be a concern in memory-constrained environments. Another approach is sorting the dictionary lexicographically and using binary search to find the shortest prefix for each word. This method has a time complexity of O(m * log k, where m is the number of words in the sentence and k is the number of roots. While it's easier to implement than a tree, sorting the dictionary adds overhead, and binary search can become slower when processing repeated lookups. A simpler alternative is hash set matching, where you store all roots in a hash set and iteratively check prefixes of each word, starting from the shortest. This method is easy to implement but less efficient for long words without matching prefixes, as it requires multiple checks for every word. Each of these approaches has its strengths and weaknesses, so selecting the right one depends on the problem constraints, such as input size and memory limits. By understanding these trade-offs, you can choose the most appropriate solution during an interview or while solving similar real-world tasks. Great job! Today, we explored the replace words problem, summarized key approaches, and highlighted takeaways for future practice. Don't forget to like and subscribe, and keep coding confidently. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!